Anyone who's ever watched an auto race or listened to a car when its horn is sounding as it comes toward them or away from them is aware of what's called the Doppler shift. The fact that the frequency of the sound that you hear changes, whether a person is emitting that sound from the engine, for instance, in a car race, whether the car is coming towards you or away from you. It can also happen, since all motion is relative, whether you're going toward them or away from them. This is in fact the technique of measuring that frequency and comparing it to a reference that the police use as a method for detecting your speed of your car and giving you a ticket. It's also how we can determine wind speed with Doppler radar that enables us to know when there's wind shear or a tornado is coming. So Doppler shift is a very interesting phenomena, and it's got many practical useful applications. We're going to start by considering the case in which the observer who is hearing the sound is the one that's moving and not the source emitting the sound. And we're going to go through the mathematics of that here. Now, the notes have already been put up on the website for you to get, so all we're going to do here is step through them. We have a source here. It could be a horn, an instrument, or something else right here. And that horn is sending out some waves. Now those waves are probably spherical waves, but for our case we'll just consider them to be plane waves in one dimension going out. And those waves between these peaks, so here's a peak if you would, and the next peak it'd be over here, let's say, and the distance between those peaks is some wavelength called lambda. And those waves are traveling with some speed, and that speed is v. Now, that speed v is the speed of the wave. The observer is running toward that thing. Now, sound is the most common one, the one we're interested in, but let's think of water waves for a minute. The water wave, these are the crests. And if the observer was sitting here, these crests would take a certain amount of time and they would hit the observer. And the observer could determine the time that it takes for them to hit. And what he would find is that the time would depend on the distance between these peaks, that is the wavelength, divided by the speed. And 1 over that time is called the frequency. So if the observer was not moving, this would be the time it would take for the peaks to hit them. And 1 over that, or v over lambda, would be the number of waves that would hit them. But now with the observer, if the observer's moving toward these peaks, then he's going to start running into more peaks than you would expect if he was sitting still, because he's actually cutting down, if you would, that distance. So what we're finding actually is that by moving, the observer is increasing or decreasing the speed. If he's moving toward the waves, then it's as if the waves are moving faster. If you don't see this, let me give you another analogy. A baseball's traveling towards you at 60 miles per hour if you're sitting in the batter's box. But if you run at the baseball, say at 10 miles per hour, then the baseball would now appear to you to be traveling at a faster speed, say 70 miles per hour. So the time it takes to get to you would be less. This is the same sort of phenomena here. If the observer is moving toward the waves, then it's as if the wave has a bigger speed, v plus v naught. If, on the other way, the observer's moving away from the just like if you're running away from the baseball, if you run away from the baseball, the ball takes longer to get to you. It's as if it moves slower. So you have a minus sign. So the plus for towards, or more precisely than the wave, toward the source of the wave. Minus means is for away from source. Okay? Now, we now go and calculate the new time. We still have the same wavelength, lambda, but we got to divide by a new speed. And that speed is v plus or minus v naught. If you take the ratio of the original time it took the wave to the new time, then because these are 1 over the frequencies, this is the equivalent of the new frequency to the old frequency, then you will find that it's simply equal to the speed that you now have, the new speed, divided by the old speed. Now you might want to do this, and it can be done a couple different ways. You could say that f prime is equal to f times 1 plus or minus v naught over v. If the observer speed is small compared to the speed of the wave, then basically the frequencies doesn't change much. But let's say that the observer could go at half that speed. Then this would either make this 1.5 times the frequency, or if the observers go in the other direction, it would make it only half the frequency. So when v naught begins to get close to v, you can have dramatic changes in the frequency and hence the pitch that you hear. So this is how you get this formula in the textbook for calculating the new frequency. There's the original frequency, here's the new frequency, and it depends on the observer's velocity with respect to the sound. Now let's take the case where the observer's stationary and we move the horn or car toward them. In this case, it's a little different. What it is as if when the source sends out a wave and the wave starts propagating, if it wasn't moving, the wave would follow a certain distance before there'd be another peak. So there's just the first peak, let's say, and this is the second peak that it emits. And if the source was stationary, there would be a certain distance, which we call the wavelength. But because the source has moved this far, let's say, in a given amount of time, because it has a certain speed, and because there was a time between the peaks, it has closed some of that distance. And so it's effectively shortened the distance between the peaks. That is, it has an effectively shorter wavelength. Now, from this diagram, we can find out what that wavelength is. The original distance between the peaks was lambda. But if this thing is moving toward the observer, it's reduced it by this distance, the speed of the source times the time between the peaks, which would be Vs times t. Again, minus is toward observer, plus sign is away. From observer. If it was going the other way, then the distance when it emits its peak, let's say it goes over here somewhere, then when it emits the peak, there's now a greater distance, and it's the distance that it added because it moved away. So the wavelength would get longer, and so you'd have the plus sign. If we take the ratio of the new wavelength to the old, we get lambda minus plus the speed of the source times the time divided by lambda. The lambdas cancel, we get a 1. We get the speed of sound t over lambda, but remember t was the original frequency, is 1 over the period. And that time we're talking about was the original time between peaks, so that puts the f on the bottom here. But this wavelength times frequency is the speed, v, of a wave. So we get 1 minus plus the source speed divided by the speed of the wave. And if you want to find a common denominator, we get the speed of the wave minus plus the speed of the source divided by the speed of the wave. To put it in terms of frequency, we multiply the top by c and divide by c. That's just multiplying by 1. C times lambda prime. So when you do that here, if we do that, we get V minus plus Vs over V. And I should say something. There's a slight error here in this thing. This doesn't need to be C. That would be if it was light. This needs to be V. So lambda, the speed divided by lambda is equal to V. And the speed divided by lambda prime is equal to the frequency primed. Put that in there and we get the frequency divided by the frequency primed is equal to this. So the new frequency over the old frequency depends. Notice that the formula is different depending on whether you move or whether or not the source moves. Didn't we say that all motion was relative in physics? Well, it turns out that this formula obviously has a preference based on who's moving, and that's because the medium that carries the sound or water or other mechanical waves is a preferred reference frame. It's motion with respect to that medium. This is an interesting question for light because light has no medium, and it's an interesting question in modern physics, and Einstein came back and actually looked at this in dealing with what he called relativity. But unfortunately we don't have time for that, nor is it in this course. What's important is to note that it does depend on which one you're talking about moving, and you could have both moving, both the source and the observer. You can combine the two formulas to produce a single formula that handles both these cases, which I give you and which the book gives you, which is this. The frequency that you detect depends on the frequency that's emitted. On the top, it depends on the speed of the wave, and it depends on the speed of the observer. And on the bottom, it depends on the speed of the wave, and it depends on the speed of the source. So let's say you have a 200 hertz wave emitted by a stationary source to an observer moving toward the source at 15 meters per second. And we'll assume that we're at regular temperatures for sound, and that means it has 343 meters per second. So the new frequency would depend on 200 hertz. It would be 343 meters per second, and you're moving toward it, so it's going to increase 15 meters per second divided by 343 meters per second, but the source had no change. So there'll be a slight increase by 15 over 343 parts. And I'll let you punch the calculator to determine that. All right, that covers the Doppler shift.